Alright, so this is the final chapter. Oh, no, final section in chapter 7. Not the final chapter. It's not June. So we are going to do the rest of, well, 7.5. But before we do that, I want to take a look at the front cover of 7.5. And we're going to fill out some of these bubbles. And by the end of this section, we will fill out the rest of the bubbles. So what I first want to do is fill out quadrilaterals. Now, I mean, I'll talk as I write in some shapes. The goal about these bubbles is to have a clear reference of shapes that we already know, or shapes that we have worked with like parallelograms and quadrilaterals, and to have like their key information easy for us to see, like have easy access to it so you don't have to flip through your paper to see them. Or flip through your note packet to see them. So that's the goal, and I'm going to fill out the key information for each one. And I think I'll do it in green because I don't use green too much. So for quadrilaterals, this is any four-sided polygon. For parallelograms, the key thing to know is that it is four-sided polygons that have opposite sides parallel with each other. That's the key thing for that. For rectangles, it is having all angles congruent and having its diagonals be congruent as well. For rhombuses, it is having all sides congruent and having its diagonals be perpendicular. And then squares, it's everything from rectangles and rhombuses. So all the special properties from rectangles and rhombuses go into squares. And this is just like the key information. Everything that applies in parallelograms, like everything we learned in 7.2 and 7.3, still apply to parallelograms. Like opposite sides congruent, opposite angles congruent, like all that stuff. That still goes along with parallelograms. But I want to just write out the key things that make these shapes what they are. And by the end of this video, we will have the rest of the shapes filled out. Now, the one that we're going to start with today for 7.5 is kites. Kites only have one subsection of it, which is right here. And we'll fill it out in a bit. But we gotta actually work with kites first. But what is a kite, you might be asking? Well, a kite is a quadrilateral that has two pairs of consecutive congruent, consecutive congruent sides. Now we know what consecutive is because we keep hearing this word so many times as we are been going through this unit. Consecutive congruent sides, I guess I'll circle this. It's talking about sides that are congruent to each other that are right next to each other. So on a kite, it's going to look like this, with the two short segments being congruent to each other and on the like right next to each other. Same with the long segments. They're right next to each other with an angle, not angle. Yeah, I guess an angle. With an angle just kind of blocking out that connection that they can make. So consecutive congruent sides, we're sides that are right next to each other. This is the defining feature of a kite. And it doesn't really show up in any other shapes besides, like a rhombus where all sides are congruent, or a square which has all sides congruent. So you can kind of make a little connection with a rhombus with a kite, but it have to be all sides congruent. And that's not usually the case unless if we're talking about a rhombus in particular. So you could kind of say that rhombuses are all rhombuses are kites, but not all kites are rhombuses. Like that sort of deal, like how we could do with a square and a rectangle. With kites, we have two theorems that go with it. One that goes along with its diagonals and the other goes with opposite angles congruency. With the diagonals, it's stated that if a quadrilateral is a kite, then its diagonals are going to be perpendicular with each other. That's not how you spell diagonals. And remember that perpendicular means creating a 90-degree angle, which we have in this picture right here. We have a 90-degree angle created right there. So that means if ABCD is a kite, then that would mean segment AC is going to be perpendicular to BD, creating that 90-degree angle in its diagonals. And if we're going to be talking about opposite angles congruency, we can say that if a quadrilateral is a kite, then exactly only, well, I'll just put exactly one pair of opposite angles will be congruent to each other. Big emphasis on the one pair of congruent angles, because it is only one pair of opposite congruent angles. Noticing in our picture right here, we have angle C and angle A. Those are the opposite congruent angles. So that means if ABCD is a kite, or wants to even be a kite, then that's going to mean angle A is going to be congruent to angle C, but angle B will not be congruent to angle D. I'm getting out the red marker to put that big X right there. So angle D and B cannot be the same angle. If it was the same angle, then this would end up being a parallelogram. Actually, no, this would end up being a parallelogram. Be a full kind of amalgamation of it, but we're not worried about that right now. I think at that point it might be a square. Either way, with those two theorems, we can start doing problems with kites. I just ripped the whole page of trapezoid theorems that we're going to go through. And the next page. Oh, God. What a great time. It's a little late. It's 7:13 and I just got home. I went to my grandparents because it was a snow day today. I don't think we should have had a snow day, but it's whatever. Anyways, example 1. We need to find the measurement of angle C. Seeing angle C right here, there is nothing in that angle that we have. So taking the theorems that we have, this angle is going to be congruent to this angle, and let's just give it a variable. So I'll put X there. And remember from 7.1, quadrilaterals have an interior angle, like the sum of the interior angles for a quadrilateral is 360 degrees. So I can set equal all the interior angles to 360, so I'll have 80 plus 50 plus x. So I'd end up with 360 is equal to 130 plus 2x. Getting that 130 to the other side, I'd end up with 230. That's equal to 2x. Divide by 2, and that x is going to end up being 115. Which would mean that is the measurement of angle C. It's not too bad. Kites are the easy part for this unit, or this section. The hard part, I wouldn't even say it's the hard part, but the more complicated and more loaded shape is the trapezoid. But before we move on, let's fill out this part with kites. So for kites, I would say that it has 2 pairs of consecutive congruent sides. That's what I put for kites. And yeah, that's the defining feature for kites. The next one, which is the final one, is trapezoids. Hint, hint. I already talked about trapezoids. And we'll keep the other box down, or other circle down there kind of blank for a second. I gotta go spit out my gum. If you're watching this now, hope you had a good snow day at this point. 3rd and 4th hour, I think, because I did kites on Wednesday. You should be watching this part right now, in class. We're doing trapezoids today, and we're going to do the rest of this. You better, for the life of you, actually pay attention for this, because I do not plan on going over it in class. So you better learn about trapezoids today. Good luck. So, given the trapezoid right here, ABCD, there is some things that we can pick apart and kind of put together for a trapezoid. I got to flip to the right page in my notes for trapezoid. So I'm giving you guys the correct information. I'll give the definition first, and then we'll fill out this stuff right here. So the definition of a trapezoid, we have a quadrilateral with exactly 1 pair of parallel sides. That's what a trapezoid is, and those sides would be up here on our figure. And speaking of our figure, we're going to kind of put together these 3 terms on our figure, and I'll be using 3 colors to kind of illustrate and color it in. We'll use green for the base, and I will start with the base, I guess, first. What is the base of a trapezoid? Well, it is the parallel sides of a trapezoid. That's considered the base of it. The 2 parallel sides are the base of a trapezoid. So in our case, right here is a base, and right here is the base of our trapezoid. For legs, the legs of a trapezoid, I'm going to put them in blue. They are the 2 other segments. So 2 other segments of trapezoid. They do not have to be congruent. They do not have to be congruent. I'd put a star right here. The legs do not have to be congruent. They can be different sizes. So they can, like, look at the picture right here. One is definitely longer, like CB is longer than DA. We can say that right now. So they don't have to be congruent to each other. They will not be parallel either, which is why we don't have any parallel marks. If they were parallel, then this would end up being a square or a rectangle. So they are not parallel. They can be different sizes, so that's good. The base also will not be the same size, at least for like a traditional trapezoid. Once you start getting the same sized lengths, then things start turning into different shapes, being more specific. So not congruent, not congruent. I think we're good with that for right now. Base angles. These will be in red. They form off of the base of the trapezoid. There are two pairs of base angles. And there will be a pair at the top of the figure. In our case, it'd be C and D. And we'll have a base at the bottom at B and A. So this is the base, the legs, and the base angles. Those are terms that we kind of seen already in geometry when we talked about isosceles triangles. Now, we can say that there perhaps is some kind of isosceles trapezoid, and this is kind of where I'm getting at, because there is a special case of trapezoids where there may or may not be legs that are congruent with within this trapezoid. This is known as an isosceles trapezoid. And we can treat it kind of similar to how we did with isosceles triangles, where the legs are going to now be congruent. And this is classified as a special trapezoid, which is why we have the extra bubble that goes off of the trapezoid. This is going to be for the isosceles trapezoid. So I guess we can fill in this bubble for right now, but I'm not going to. So the difference between the isosceles trapezoid and just a regular trapezoid is the fact that we have congruent sides, congruent legs. Like, these are the legs. I'm going to outline it in blue just like how I did already. Like, these are congruent. I'll outline the base in green, like how we did at the top. That's the base. The base angles are still parallel, or the base angles. The base sides are still parallel with each other. They're not the same. They're not congruent, but they're parallel. And we still have base angles to work off of. The only difference is that our legs are going to be congruent. If our legs are congruent, we get the isosceles trapezoid. So maybe we can write an if-then statement down here. If legs are congruent, then we get isosceles trapezoid. It's good to have an if-then statement and kind of clarifying it. But that is our two special kinds of trapezoids that we will be working with. And we can distinguish between whether we have an isosceles trapezoid or not. Given the example that we have, I have the trapezoid ORST, and I need to decide whether it's an isosceles trapezoid or not. Okay. So, first off, I need to check if first thing, slur my words, I need to check if this thing is a trapezoid at all. What is the defining feature of a trapezoid? Well, let's look at the definition. It states that we need exactly one pair of parallel sides, those sides being on the base. So I need to check if my base sides are parallel on my trapezoid. So I need to check if RS and OT have the same slope. So I'm going to I can either count this or do it by slope formula. I'll count for RS and I'll do the slope formula for OT. So let's count the slope. So I rise 1 from R and I go over 2. So I should have a rise of 1 and going over 2. And that'll be my slope for RS. For OT, I'm going to do it the distance formula way. So I need to do y2 minus y1 over x2 minus x1. And let's say that this is going to be my x1, y1. This will be my x2, y2. So that means I should have a 2 minus 0 over a 4 minus 0. That'll end up being 2 over 4, which is 1 over 2. And that is my slope. RS has the same slope as OT. So that means ORST is a trapezoid. I guess I should write steps for what I'm doing. So, first step, step 1. Find out if your shape is a trapezoid. Check if the base sides have the same slope. All right, number 2. Step 2. Now we're going to check if this is an isosceles trapezoid. So I'm going to check if legs are congruent to see if we have an isosceles trapezoid. So I need to check if these are congruent with each other. I will do a little... Now, to check if these legs are congruent, which the legs are going to be ST and RO. That's our legs. I need to do the distance formula in order to do that. So maybe I'll do a point out distance formula. I hope you know the distance formula by heart at this point. If you need a refresher, it's y2 minus y1 squared plus x2 minus x1 squared, and it's all under a square root. Make sure you keep everything under a square root as well. And let's do the distance formula. I'll do it for, and you have to do the distance. Actually, we don't have to do it for one of them. In the case of RO, since it is on the axis, the y-axis, and it's vertical, we can count how far away R is from O. You can only do this when we are going vertically, or when we can count vertical, or if we can count horizontal. You cannot do it diagonally, but I can do it for this case. So if I count from R to O, I'm going 1, 2, 3 units. So that means I have a distance of 3. Let's see if S to T is a distance of 3. So I got to do distance formula. Since I have T already as x2 and y2, I'll put x1, y1 at S, and now let's find the distance. So 2 minus 4 squared plus 4 minus 2 squared, and I put it all under a square root. I will end up with a negative 2 squared plus a 2 squared. Put it under a square root still. And then I have a 4 plus 4, which will end up being the square root of 8, which comes so close to being 3, but it's not. I think it might be like 2.8. Let's check. I think it will be 2.8. Nope. Hold on. Square root of 8. I don't have my calculator on me. It is 2.8. Ha ha ha. Look at me. I'm so smart. So they are not the same slope. And I'll point that out. Not the same slope. So that means ORST is only a trapezoid, not an isosceles trapezoid. And when you do these problems, I want you to be specific. Like, you gotta first find if it's a trapezoid or not. And then also, if it is a trapezoid, you gotta tell me if it's an isosceles or not. If you end up getting an answer where it's no, tell me that it is not an isosceles trapezoid. If it is an isosceles trapezoid, just tell me that it is. I think that makes sense on how I asked. I think you should be fine. All right. Moving on. We're going to the ripped pages now. The one where I split in half when I I ripped this page super hard apparently because it went straight through. All right. So we got some theorems to go through. Now these theorems kind of look familiar because they're all based off of what we learned already with isosceles triangles, but now we're applying it to trapezoids. So theorem 7.4 deals with the base angles of the trapezoid. It states that if we have a trapezoid that is isosceles, then each pair of base angles are congruent. So that means in our picture, if ABCD is I'm going to abbreviate isosceles trapezoid with an IT. We'll do ITP. ITP for isosceles trapezoid. Then I will have angle B be congruent to angle C and angle A be congruent to angle D. Likewise, how we had a regular theorem for base angles with isosceles triangles, we also have a converse for that. The converse of that being if a trapezoid has a pair of congruent base angles, then it is an isosceles trapezoid. Key word is a pair. You do not need both pairs to say that it's an isosceles trapezoid. You only need one pair to say that this is going to be an isosceles trapezoid. In our case, in the picture, I have angle A is congruent to angle D. So I can say if angle A is congruent to angle D, then ABCD is an isosceles trapezoid. If I was given BC being congruent to each other, I could say if angle B was congruent to angle C. Note that you only need one pair in order to make it work. So that's very convenient. You don't need both pairs. So that's nice. There's also a diagonals theorem for trapezoids. It's kind of cut off, but this is the isosceles trapezoid diagonals theorem. And it states that if a trapezoid is isosceles, if and only if its diagonals are congruent. So that means ABCD is an isosceles trapezoid if AC is congruent to BD. So that means, I don't know. I'm trying to like, I'll put a mark like that or something on the picture. It's not really congruent mark friendly, I guess. But that means our diagonals are congruent. That's nice. So we can use that to our advantage. For example 3, use the trapezoid EFGH for the following problems. Likewise, I can say that, well, we'll do A. If EG is equal to EF, is trapezoid EFGH isosceles? Well, let's find out. EG is this segment right here, and EF, HF is this segment right here. So it's the diagonals of this trapezoid. And it says that they are equal to each other. And remembering how congruency works, we can flip congruent marks around by saying it's equal. So I can say that, yes, EFGH is an isosceles trapezoid because its diagonals are congruent. Looking at B, it says that if angle HEF is 70 degrees and angle FGH is 100, is the trapezoid EFGH isosceles. So HEF, that's this one. We can put 70 here. And FGH, put that here. 100. Is this isosceles? Explain. No, it is not isosceles. Because these angles are not a base pair. They are across from each other. They're not a base pair. They're not base angles. They don't form a pair together. So no. They are not a base pair of angles. They aren't even congruent. So EFGH is not an isosceles trapezoid. Simple enough. All right. Not too shabby. When you do your problems, I want you to kind of explain your reasoning. Do not give me I know I said before, you could give me the number of the theorem. No, I want you to actually explain your work for it. Last page of notes for chapter 7. Mid-segments. So we did a lot of work with mid-segments, unfortunately, for like the last week of before Christmas break. Remember mid-segments? It was when we had to deal with stuff like this, like triangles that looked like this. This is when we had triangle day, by the way. Mid-segments appear on trapezoids. It kind of looks like cake layers. I'm gonna be real, which right up my alley, like straight up, because I love baking. You guys know this. Do not hound me for brownies. Maybe Thursday. We'll see how I feel. I shouldn't have said that. You better not remember. You guys won't remember. Anyways, this appears for trapezoids, and we have mid-segment theorems that go with it. With this being 7.17. The trapezoid mid-segment theorem. So we can state that the mid-segment of a trapezoid is parallel to each base, and its length is 1/2 the sum of the length of the bases. All right. What the heck does that even mean? It's good to write out the words for it, but I have a spot right here that will put the general equation for that. Now, the general equation that we make will be based off of this figure. Every figure has its own variables. I have the faith that you can change out your variables in cases that you need. Like, not every trapezoid is going to be A, B, C, D. Some might be P, Q, R, S. The mid-segment is not always MN. It might be like a QR or like an ST or something like that. You need to be able to switch out the variables so you can apply the formula. This formula that we will be working with will be having the mid-segment be our main focus, so MN. And we are going to set that equal to the sum of the length of the bases. So the bases that we have is AB and DC. So I'm going to put AB plus CD or DC adding together because it's the sum of the bases, and it's 1/2 of it. That's the mid segment. It's 1/2 of the sum of the bases. So I'm going to put that under 2 because that's 1/2. This is the formula for mid-segment trapezoid work. And I'm going to apply it to example 4, where we are given some lengths to work with, and I need to find the mid-segment of MN. Let's do it. So I have MN right here. Let's put MN is equal to 12 plus 28. So 12 plus 28. And we got to put that over 2. Great. 12 plus 28, I believe, is 40. So I'll have 40 is over 2. And that is equal to 20. So MN is equal to 20. Great. It's 20 inches. Notice, I want you guys to take a note as well, because there's a pattern that goes along with this one. Going from 12 to 20, we have 8. Going from 20 to 28, we have 8. This pattern kind of follows through for the lengths. So keep that in mind as you work. All right, so we found the length of MN, and we have the length for each of these segments. Let's just say, in our case, I don't know what PQ is, but I know what MN is. And I need to find out what the length of PQ is. Let's do that problem. And I do not want you guys to skip this part because it is important. We are going to find the length of PQ. Even though it's right here, I'm going to block it out. We don't know what PQ is. We're going to find it with these two segments. I will do it in blue. All right, so PQ. I'm going to scribble that out. We don't know it's 12 yet. But I know MN is 20 and SR is 28. What am I going to do with this? I'm going to plug in what I know to my base formula. PQ in this case is going to be AB, SR is going to be CD, and MN is going to be MN. So I have 20 is equal to PQ plus 28 over 2. And what I'm going to do is try to get PQ by itself. So I'm going to end up multiplying the 2 on both sides to get rid of this fraction. So I will end up with a 40 is equal to PQ plus 28. And then I can subtract this 28 over to the other side to get PQ by itself. And now I'll end up with 12 is equal to PQ. Being able to find any value out of this cake stack of numbers is important because sometimes you're going to be given just 2 layers, like a middle layer and the bottom layer. And you're going to have to find the top, or the top layer and the middle layer, and you're going to have to find the bottom. Being able to use this formula for finding any segment is important. Keep this in mind so you can do this on your homework. The last thing that you will be asked to do is to maybe work on a graphing problem, trying to find the mid segment on a graph trapezoid. Okay, so 2 ways we can work with that. Flipping it over to the next page. We could do it 2 different ways. First way is to all right. So there's 2 ways of doing this. We could either do it the formula way or do it a different way. We're going to do it both ways. I'm going to do it the formula way first. So I'm going to split off, I guess, the segment right here. This is going to be the second way. This is going to be the first way. All right. So step 1, we will find out the length of TU and SV. We got to find the lengths of them, find the distance, and we got to use distance formula. Okay, we'll use black still. So I'm going to do TU first, and since these are on diagonals, I can't count at all. So I will do, let's just say, let's do 2 minus 10 squared plus 12 minus 8 squared, square root it. I will end up with negative 8 squared plus 4 squared. That's the square root of 64 plus 16. 64 plus 16. I don't know that off the top of my head. I should because of like Minecraft or something, but I don't. This is the square root of 80. That's TU. Then we got to do SV. SV is going to be the square root of 2 minus 6 squared plus 2 minus 0 squared. That will end up being negative 4 squared plus 2 squared, being the square root of 16 plus 4, which is the square root of 20. So I found TU and SV. Now I can do step 3. Not step 3, step 2. We'll move step 2 over here. And now that's going to be using the formula, find length of YZ. Formula as in mid-segment formula. All right. So all I'm going to do now is use our mid-segment formula to find what YZ is. So YZ is going, oh, I don't need to put dots right there. I can just do that. YZ is going to be equal to the square root of 80 plus the square root of 20 over 2. That's going to end up being something that I don't know right now. I have to get out my hold on. We'll bust out the calculator. All right. Well, hold on. Let's do it in my head for a second. That's not the right page. All right, let's play some bets. Okay. Square root of 80 is close to 9. Plus the square root of 20 is like 4.2. So I'm going to say like 6.6. I'm just now typing this into the calculator. I'm going to say 6.6 is going to be the answer for this formula. And that's like roundabout answer for it. I don't know if this is true or not, but we'll find out. Evaluate, please. We get 6.7. Oh, that was so close. Let's go. It's around 6.7. I'm doing it with square roots, but that was pretty good. Good job. There's a different way of doing this. You could do it a different way. If the points were flush, like even points on the grid, you could just find like the legit distance of y to z. But I wouldn't do that, at least in this case, because z is kind of in the middle. You would need to like directly find. Okay. If you wanted to do this a different way, you could find the midpoints of y and z and then just do the distance formula from there. But that's something that it take the same amount of work, I think, as just doing this. So I just do this because you're going to be using the mid-segment formula anyways. Well, not the segment formula. No, you will be using the mid-segment formula anyways, and the distance formula. Might as well just not even use the midpoint formula. There's no second way. I was joshing you guys. One thing that we forgot to do is fill out this part at the end with trapezoids having exactly one pair of parallel sides. Those being the base sides of a trapezoid. I've got to move it down. And then the isosceles trapezoid, that having its legs being congruent. Now, I guess just talking my sake, this is like very base cases of the tree that we have right here, because with some, like, I think I mentioned it more in kites than trapezoids, but with kites, you can eventually make it to it becoming a rhombus, and the rhombus goes to a square. So like kites, you could kind of gradually make its way to a rhombus. Same with trapezoids almost. You can kind of make its way into either like a rectangle. You could you can make its way closer to a rectangle almost to a instead of a rhombus. So in reality, I should have switched the places so that I could kind of make like a do arrow going that way. Instead, it's going to go like like all the way over here, and then we'll have one going all the way over here. Like, you can make cases going those ways for both of those shapes, but all in all, everything most likely will just become a square when you start getting to like super specific cases. But in general, this is how the tree goes. For quadrilaterals, everything's pretty connected, which is honestly super cool. Everything can end up being a square at some point. I find that fascinating. And before I stop talking, because you guys can't hear enough of my voice, I'm going to pull up the homework assignment. Now, I'd be fancy and just pull it up on my computer and like screen record, but I don't want to right now. So I'm going to go through the assignment a little bit. Because this is a biggie one. I haven't given a big assignment in a little bit. And I know your test review is also going to be given. Well, not at this point on Friday because of the snow day. It'll be given on Monday. Speaking of the test, if we do have school on Friday, it's going to be on Wednesday. But with this, I want you guys to fully like practice and go through and take your time, especially with 7.5, because that deals with a lot of trapezoid stuff. I'm going to assume that kites kind of went easy and you understand kites super well. Trapezoids is what I think I focused on the most when going through making this. Like, I have a lot of mid-segment stuff, finding like the value of X and finding the mid-segments of a trapezoid. I have a lot of those problems. I have graphing ones that go with it. And then I also put a lot of 7.4 stuff into it where we need more practice on giving like specific names of quadrilaterals. Like I want, like for this one, yes, it's a rectangle or it could be a square, kind of 23 as well. I want the most specific shape that you can name it. And I have some graphing mid-segment ones down here. This one was what we did like at the start of trapezoids where I just figure out if it's isosceles or not. And then I have you guys working a lot with rhombuses, rectangles, and squares still. Trying to deal with its properties, keeping that in mind. It is a lot of problems, but once you know the anatomy of a rhombus, rectangle, and square, these problems aren't going to be too bad that you can actually do them. And then having you guys do more exercises on giving the best name for a quadrilateral, parallelogram, rectangle, rhombus, square in these problems, like giving its best name for that property. Because it's super important to be able to recall this stuff. I'm spitting everywhere. It's important to recall this stuff because it's going to come up a lot on your test. So giving you guys more practice to work on it is important for my sake and your sake. Because it's just handy to know. And it's also kind of review for your vocab quiz. Because knowing the properties and how they work, especially for like these ones right here, that can help you memorize, oh, that's a property of a rhombus, having opposite angles congruent. That's definitely one. And having the diagonals bisect a rhombus. That's so true, because now I'll have 53B right here for A as well. And then I'll have 53 down here for C, for both of those ones in C. Oh my God. I gave you some of the answers right there. But any case, like that can help you remember some terms, which is good. I'm going to stop yapping. Hope you guys have a good weekend. This will be due on Monday. I want the whole thing done on Monday. And we'll go over, I say probably most of it on Monday as well. Have a good weekend.